Alright, so tonight's video will be fairly short and sweet. It's all about a guy by the name of Chev. Okay? And the idea here is that when we don't know something about a mean, frequently we'll find a sample average, obviously. We'll just go, hey, look, X bar is equal to blah. We'll take a sample, maybe say of 30 things. We'll average, maybe we're going to find the average weight of a frog, green tree frog or something. Genus number, whatever. Okay, we'll find some. Do a nice random sampling of them. We'll find the average 27 ounces or something. That's great. Maybe that's what it is, 27 ounces. How close are we? I don't know. Well, we need to have an idea. So what we're going to do is make a confidence interval. Okay? Now, a confidence interval is something you've heard of before. It's frequently, every time an election comes around, let's say something like, so-and-so has an approval rating of 54% with a margin of error plus or minus 3 percentage points. So plus or minus 0.03. Meaning that somewhere between 51% and, well, this is actually a P because it's a percentage, but whatever, and 57%, we feel very confident that's in there. And we'll talk about, is it 95% confidence or whatever confidence we happen to be in. Okay? And we'll talk a little bit more about this later on. However, this is all fine and dandy. We have ways of doing this and to be more exact if our data is nice and symmetrical. For instance, if everything is nice and look at this bell curve, which we'll talk about later, we're going to call it the normal distribution. But even if it's not the normal, it could be a binomial. They are also symmetrical. And so if your distribution is symmetrical, well, then we can be a lot more accurate because we know what to expect. Well, this fellow by the name of Chev came along and said, listen, it'd be kind of cool if we didn't matter what the distribution looked like. If it looked like this, like that. And by the way, we call this skewed to the right because it's like you pulled it out to the right. So we call skewed to the left. Sometimes this one would be referred to as negatively skewed. This one would be positively skewed. Okay, it's the direction that you pulled it out towards. This is Lake Oswego's home prices. Lake Oswego. Right, and then there's one lousy house in town that only costs $300,000 or something, right? So it really pulls the property value down. This is LeBron moved to my little town of St. Helens out here, and then this is their incomes or something, okay? He's kind of skews it out that direction, okay? The idea is that if the data is not perfectly symmetrical, could be kind of a goofy shape like this, okay? We need a way to say, listen, we feel fairly confident the mean is here, but we need to know from where to where. Or another way of taking that and turning it on its head is saying, listen, what we really want to know is between here and here, what percent of the population will be in here. So one that is nice and symmetrical that I happen to know, fairly well by heart. Average woman in America is somewhere in the neighborhood of 65 inches tall, height-wise. And there's about a 2 standard deviation. Oops, 71. Learn how to add, you moron. You with me? So I just counted off by standard deviations. So in a situation like this, we always talk about this. You've probably seen this before. 68% on a. This is what we refer to as the empirical rule, and it always works for all symmetric distributions. It doesn't have to be normal. It can be anything. Approximately 68% of the population lies within 1 standard deviation of the mean. If you go out 2 standard deviations, that's out to 5.1 and 5.9, then 95% of the population is between those two. And if you go out 3 standard deviations, this is 99.7% of the population are within 3 standard deviations of the mean. Okay? That's weird. That's why it's weird when you see a gal who's like 6'3" or something. That's freakishly tall for a girl. That's 5 standard deviations above the mean. That's freakishly tall. So that's why whoa, what did I just see? Exactly. This is why no one blinks an eye if a girl is 66 inches tall. Well, it's about what everybody is. Okay, cool. All right, no problem. Okay. This is the empirical rule. It's amazing. It's wonderful. And when we get to the normal distribution, we can get it down even tighter than just saying about those values. Okay. But here's the problem. If it's not that way, we need a way to be able to say, listen, maybe our data looks like this. So here's my average, cool, and maybe I know my standard deviation, and I'm going to use SX, although I know your book, we're going to talk about that in a minute, how they write it, and I don't really care for it, but whatever. But let's say we go out, like say, I don't know, 2 standard deviations here. That's kind of ugly, I'm sorry, let's back that up a little bit. Let's say we go out 2 standard deviations on either side of the mean, okay? That's, say, from here to here. Well, this thing is so much more variable because of the way it's shaped and goofy. I'm not going to be as exact as I was before. So it's not going to be 95%. It's going to be less than 95% because this data is always going to be more spread out. It's a little confusing. So old Chebyshev came along and he said, listen, we've been doing this. We've been taking X bar and we subtract I'm going to say K standard deviations. In other words, 1 or 2 or 3 deviations. And then we know that pinches this unknown mean. Again, we don't know the actual average. If we did, no one would be doing statistics. You just tell me what the average is, and I'd be like, that's cute, thanks. Okay? Now, that's great. Now, I will say this. Your book uses this terminology instead. They use sigma, which I don't care for because you will never in practice ever know sigma. Okay? So I'm a little fed up with it, but whatever. This K is the number of standard deviations away from the mean. Standard deviations from the mean. Okay? So in here, so between here and here, there is at least 1 minus 1 over K squared percent, times 100. Times 100% of the population. Now, what does that mean, Jay? Well, let me clue you in, friend. Okay? So, within 1 standard deviation. So, within 1 standard deviation, it's 1 minus 1 over 1 squared, which is 1. 1 minus 1 is 0. So there's at least 0% within 1 standard deviation. Boy, that's not helpful, friend. What if I did within 1.5 standard deviations? I'm glad you asked. How about 1.5 standard deviations? I don't know. Let's find out. So that's 3 halves here, squared. So it's going to be 1 minus 1 over, and then that's 9/4. So it's going to flip over. It's going to become 4/9, and 1 minus 4/9 is 5/9, which is 55%. So at least 55% are within 1.5 standard deviations of the mean. You're like, what about 2? I'm glad you asked. 1 over 2 squared is 1 minus 1/4, so is at least 75%. So listen, the cool thing is Chebyshev does not counteract or contradict the empirical rule. This works for all distributions, okay? It was made particularly for ones that we don't know how they're distributed and or ones that we know they're skewed. So I can't be as sure because they're not nice and symmetric. So there's at least 75%. Last I checked, 95%, which is what the empirical rule would say, is at least 95%. It's bigger than 95%, okay? So it's not very difficult. That's how it works. Now let me show you a few book-type questions that they ask. Maybe something along these lines. Oh, piddly diddly. I'm going to make one up. So, X is this random variable. It has this distribution. These are the things that it can be. Notice this makes it a, wait for it. Come on now, you got this. What is that? That's a discrete distribution, correct? That's what I was going for. And so what it says is the following. It says, a problem like this. Let's do the following. Let's find the expected value, and let's find the expected value here. So the expected value, well, we talked about this previously. It's 2 times 1/6. Oops. Well, I guess that'll work. Cool. So that's going to be 2/6, which is 1/3. This is 3/3, so that's 1 plus 4/3 plus 5/6, which is, what is that? Well, I don't care. This is 5/3, and 3/3 is 8/3 plus 5/6 is 16/6 plus 5/6 is 21/6. Yay, which is 3.5. This is our expected value. Okay. So what would the expected value of x squared be? Remember, to do this, to find this, we need to find out how many standard deviations we have there. So we need to know what the standard deviation is. So it'd be 2 squared times 1/6 plus 9 divided by 3, I guess. I'll just kind of cheat a little bit. Plus 16 divided by 3 plus 25 divided by 6. Just did the squaring in my head. 79/6. So that's 79/6. So then, remember, sigma squared is this guy minus this guy squared. So 79/6 minus 21/6 squared. I don't know, I can't do math. Minus 11/12. That is sigma squared. That means that that is the square root of that is my standard deviation. So square root of 33/6. Cool. Okay, now, what does that tell me? Well, it tells me I know this, and I know x bar is 3.5. Cool. So it says the following. So it wants to know, yes. So it would like to know, so our standard deviation is the square root of 33/6, which I don't know what that is. So let me get one of these numbers. 0.957. Okay. 0.957. So if someone asks you, hey, listen, I want to know what's the probability. So our average is 3.5. I want to know 3.5 plus or minus 1.2. Okay, let's just say something like that. Someone gives you this number here. So what's the probability of that? Well, I don't know. How many standard deviations is that? So k would be equal to 1.2 divided by 0.957. Oops, what am I doing? So it's about 1.25 standard deviations. So my boy Chevy Chev would say, listen, there's at least 1 minus 1 over 1.25 squared percent of the population between there. About 36%. There's at least 36% of the population between here and here. That is from 2.3. It's a mu up to 4.7, I guess. Yeah. So that's an example of one that you might see. Here we go. Here's another one here. The total time measured in units of 100 hours a teenager runs her hair dryer over a period of a year is described by this continuous random variable, where x has the density function. Remember, it's time, so for heaven's sakes, obviously, it has to be a situation where it has to be continuous, because, you know, that's just how it works. Okay? So notice that she never uses it more than 200 hours. That's what this is saying, because they're units of hundreds of hours. Okay, so that's what that's saying to me. So it wants to know this. Use the theorem in 4.6 to evaluate the mean in the random variable of 60x squared plus 30x equals y. Nice. Okay, so y equals 60x squared plus 39x. Cool. So what we want to know is, what is the mean of the random variable y? And that's what I want to know. Okay? So let's check this out. Okay? Now, we talked about this previously. What happens when you do these things? Okay? So if you go back in 4.6, we said, well, let's see here. First of all, this right here, the expected value of 39x is equal to what? It's 39 times the expected value of x. So I'm going to find the expected value of x. Now, what is this right here? Well, this, the expected value of 60x squared, right, is equal to 60 times the expected value of x squared. And then we're going to add them together. So let's do this. So to find the expected value of this, how are we going to do that? Okay. Well, because this is given in two pieces, we got to find the whole area there. So we need to do the following. We need to find the expected value of x. And to do that, we're going to take x times our PDF from 0 to 1 plus x times our PDF from 1 to 2. Let's see what happens here. Well, this is x squared, of course. And the integral of x squared is x cubed over 3. So that's 1/3. And then here, this is going to be 2x minus x squared. So that's going to be x squared minus x cubed over 3 from 1 to 2. Boy, I can't do that in my head. Two-thirds. Cool. Hey, look at that. Oops, look at that. I didn't hit shift hard enough. Look at that. The expected value of x is 1. Cool. So what does that tell us right here? 39 times that is going to be, well, 39. Now, how do I find the expected value of x squared? Well, I do the same thing, except wherever I saw an x, I'm going to put an x squared in there. So it's going to be x squared times my PDF. And then it's going to be x squared times my PDF. That's x cubed. So that's going to be x to the 4 over 4. 0, 1. And this is going to be 2x squared minus x cubed. So it's going to be x to the 4 over 4, negative. And then this is going to be 2x squared, so it's going to be 2x cubed over 3. Cool, from 1 to 2. I don't know why I didn't just do that in my head. That's a quarter here, obviously. Pro tip, by the way, this is, I didn't show it on the last one, but I normally do is I go x times parentheses 2 minus x when I know I'm going to be doing these. So there's that guy. And then all I have to do to find the expected value of x squared, just throw a squared right there. So it's 11/12. Oops, but it's not quite right. Then you got to change your limits of integration. Well, that actually is right. That's actually right. Excellent. Okay, good. Excellent. And then that's going to be 3/12. So 14/12. Cool. So up here we have 60 times that. So 1/4 plus that. I don't remember if that's what I had or not, but okay, I'll buy that. And then times 60. is 70, and then 70 plus 39 is 109. That would be the expected value of y. Okay? So, not too hard to do. Almost fun, I guess. Almost fun. Now, you're like, well, why is that in this section? Well, in this section, you're going to be using that and Chebyshev to answer some questions here. So, let's see if I can find one here that's exactly what I want. For the love of Pete. Well, let me pause you for a second while I find one I want to do. Okay, so there's another couple more problems from this section. Then I got to a couple of the Chebyshevs here, and we'll get to those in a second. So this is something that for sure you'll see in the test. It says the x and y are independent random variables. They're independent of one another. And that the variance of x is equal to 5, and the variance of y is 3. Okay? And then we want to find the variance. Find the variance of z equal negative 2x plus 4y minus 3. Okay? Well, first and foremost of all, if you want to find the variance of this guy, keep in mind that whenever you're adding or subtracting, you always add variances. Okay? And what happens when you multiply by a constant in front of this thing? What does that do? Well, it makes it more spread out. So in the video the other day, you saw this, but I'm going to go ahead and review it real quick for you. This is something if you're ever stuck and you're like, is it 2 times the variance or is it, what is it? So if you just made up some random numbers here, it doesn't matter what they are. Doesn't make any difference at all, to be honest with you, okay? Now, whoa. And then equals 2 times that fella. And drag it down. What you'll see, if you say equals variance here, oops, equals var, stupid, there you go, equals var p, and click and drag that. That's the variance. Holy crap, that's like 3,400. Wait, what is the deal there? Well, remember, when you multiply by a constant, you multiply the variance by that constant squared. And you're like, well, wait a minute. What if it's negative? Does that matter? Not a bit. Ha! Because it's negative 2 squared. How about that, friends? So this guy here then, the variance of this is going to be 4 times 5. Plus, and this is going to be 16 times 3. And then you're like, well, what about the negative 3? Listen, if you just take and subtract 3 off of everything, you don't change how spread out it is. You just shift it down. So this has no bearing on the variance. So it's going to be 48 plus 20 is 68. That's my variance. Boom, piece of cake. Now, what would the expected value of z be? Well, to know that, I'd have to know the expected value of x. So I'm making up a couple numbers here. And mu for y would be 13. Sure, why not? So then this would be, the expected value of this would be negative 20. This would be 4 times 13, which is 52. 52, you ding-dong. Now, does the negative 3 matter? Yeah, it subtracts it down. So that's going to equal 29. The expected value of z would be 29 in this case. Okay. All right, so then this one here is the last one I want to do. Oh, good grief. So this is number 76 on page 139. So 70 new jobs are opening in an automobile manufacturing plant. Of the 1,000 applicants show up for the 70 positions. To select the best 70 from among the applications, the company gives a test that covers mechanical skill, manual dexterity, math ability. The mean grade on the test turns out to be a 60 and a standard deviation of 6. Can a person who scores 84 count on getting one of the jobs? Let's find out, shall we? So the game is you're like, well, all right, let's see this thing. So we know the average was, what do you say, 60? Yep. So the average on the test was 60, and the standard deviation was 6. Now let's think about this for a minute. Here we go. Some, whatever, I don't even care what it looks like, to be honest with you. Okay, now let's count them off. So if this was 60, then we're going to have 66. Count by another 6 puts us at 72, puts another one at 78, and another one, that would be 4 deviations, would put us at 84. Okay? Now we're talking about 80 right here. Are you with me? How many standard deviations is that? I don't know. I feel like 80 minus 60 divided by 6 is equal to 3 2/3, I think. Isn't that right? 3 1/3. 3 1/3. 3 1/3. 20 divided by 6 is 18. Remainder 2. 2 6. 1/3. 3 1/3. 3 and, oh shoot. 3 1/3 standard deviations. In other words, that's my K. Are you with me? Now, if you think about this, I can also go out 6 on the other side. I think it's helpful to vision it. It's not 100% necessary, but to me, it helps me really sell it in my mind what I'm doing here, okay? And so 2 more puts us at 40, I guess. You with me? So the idea is, from here to here, what percent do we expect to find in between there? And then if I know how much is in between, I know how much is on the outsides as well. So Chebyshev said 1 minus 10/3 squared times 100% is inside of there. There's 91% is between here and here. Okay? That leaves 9% left over. That leaves 4.5% up here that test at 80 or higher. Does that make sense? And 4.5% down here. So now let's think about this for a minute. 4.5%. Well, 4.5% of 70 is what? I don't know. Let's find out. Oh, I'm sorry. 4.5%. I'm sorry. 4.5% of 1,000, rather. There should be 45 people that score that high. 45 of them. Okay. Well, we need 70 people. So pretty much everybody that scores from 80 and up can count on getting into this class. That makes sense? Because we're going to actually have to come probably down into here somewhere to get enough people to fill our applicant pool. Okay? Yeah, another one like this. If the mean is 70 and the standard deviation is 3, what's the probability that a random person would score less than less than 60? And, I don't know. Let's lay this out. Again, I always like to lay it out. To me, it just makes it easier. I just draw some random distribution. Doesn't matter. So if I come down 3, it puts me at 67, then 73 here, and then 76, and 64, 79, 82, 61, 59. Are you with me? 58, rather, sorry. So where are we at? We're talking about from right here down. How many standard, good grief, I kind of did it again. How many standard deviations is that? Well, I don't know. It's 60 minus 70 over 3, which is negative 3 1/3. Okay? Same basic premise as last time. So that what that tells me is, and it's kind of sad, and I'm sorry I did that. From here to here, again, is 91%. So to get someone from here down, it would take 4.5%. You'd have a 4.5% chance. Or another way of saying that is there's 4.5% of our population lives below 60. Okay? If you wanted to slice this up, I could write a different problem on this one. If you picked someone, what's the probability they will land somewhere between 65 and 73? I don't know. Let's find out. Okay. So if you're doing this on this problem, actually, let's make this 64. Make my life easier. Well, let's actually do this. 64 and 79. We'll make it easier on ourselves. What do you think about that? Okay. So from 64 to 76, are you with me? That's 2 deviations. So that's 1 minus 1 over 2 squared times 100. That's 75%. So let's color that in. So from here to here, that's 75%. And now you know how much is in here from 76 to 79. Well, that puts us over 3 standard deviations, yes? So if I were to do this, 1 minus 1 over 3 squared times 100, I would find that that comes out to be around 89%. Okay? Now you're like, well, wow, that leaves a total of 14 extra percent, right? Well, yes, you're right. But remember, that 14% is broken up so that 7% of it's down here and 7% of it's up here. Well, I only want this 7%. So it's going to be 75% plus 7% is 82%. That is Chebyshev. Okay? Pretty easy stuff. This section kind of reviews some of the stuff from section 4 point something. 4.3? 4.2 and 4.3. Well, it kind of reviews everything because it asks a lot of covariance, variance, expected value kinds of things. So good luck with you.